Hello and welcome to this lesson looking at forces and elasticity. In today's lesson we're going to look to understand what Hooke's law is. Now this lesson is for the AQA GCSE Separate Science in Physics in the Forces module, which can be found on paper 2. So in today's lesson we're going to describe what Hooke's law is, understand what we mean by inelastic and elastic objects, and then describe how the spring constant and the elastic potential energy store for an elastic object can be calculated from values. So this links into the following part of the AQA GCSE physics specification, the forces and elasticity section, which links in both equations and the concepts of how a force can affect different materials. So in previous lessons we've looked at the effects of resultant forces in the universe. So a resultant force can cause an acceleration for an object. A resultant force can cause energy to change between stores. Now a change in energy store due to a resultant force is called work done or mechanical work. Now work can also be done in a circuit when charge flows. That's another way you can have work done in the universe. Now, there's actually a third effect that a resultant force can cause. A resultant force can cause an object to change shape, which is what we call material deformation. Now, there are actually three types of material deformation that we can observe. The first type of deformation is called extension. Now that's where an object increases in size due to the force being placed on it. Now a force which causes an extension is called a tensile force or tension. Now just remember, when tension is applied, it will cause a force to increase in size. Now we, in this particular example, are going to define extension as a positive change. Now also just remember, because it's a resultant force, this means you need more than one force on the object to actually cause this extension. Now, the second type of deformation is called compression. That's when an object decreases in size due to a force being placed on it. Now, in today's lesson, we're going to focus primarily on extension. However, we can consider compression exactly the same, just that whilst we defined extension as a positive, we're going to define compression as a negative. Now, a force that causes compression is called a compressive force. So if you apply a compressive force to a material, it will decrease in size. But once again, because it's a resultant force, there needs to be more than one force applied to the object to cause this compression. Now, finally, the third type of deformation is bending. That's when an object doesn't change in overall size, so it doesn't get bigger, it doesn't get smaller, it stays the same size, but it changes shape. It becomes distorted. So we say it has been bent. So once again, because it needs to be a resultant force, you need more than one force to be applied to the object to cause this. Okay, so there are your three types of material deformation. Now, an object can also behave in two distinct groups in terms of these three deformations. So you've got elastic objects and inelastic objects. So an object is elastic if the object regains its original shape after the deformant forces are removed. So the deformation is not permanent. Once you remove your resultant force, the object returns to its original shape, whilst an object is inelastic if it doesn't return to its original shape after the deformant forces are removed. So the deformation is permanent. It will stay extended. It will stay compressed. It will stay bent. Now, another name for this type of material is a plastic. Now, we tend to stay away from this term in physics because the more common use of the word plastic, like plastic bottle, plastic bag, is more about the chemistry definition of a plastic. Now, in physics, objects other than polymers can also act plastically, but we like to use the term inelastic. Now, many objects have an elastic region and an inelastic region depending on the size of the deformant force that's been placed upon it. So, for example, at lower forces, objects tend to act elastically. So once you remove a small deformant force, the object returns to its original dimensions. However, at higher forces, an object tends to act inelastically. It stays deformed. So just to recap what we've just covered there, an object is elastic if the object regains its original shape after the deforming forces acting on it are removed. An object is inelastic if the object does not return to its original shape if the deforming forces acting on it are removed. And many objects are elastic at certain deforming forces, but inelastic at larger deforming forces. Now, we've got to think to ourselves, well, what would make an object elastic and what makes a material inelastic? Now, it's all to do with the atoms bonded together in the material. So in all materials, the atoms of the material are bonded together. Now, in an elastic material, when the deforming force is placed upon it, the bonds get stretched, they get altered, but they don't break. So this means when the force is removed, the bond snaps back to what it was before, the atoms go back to their original shape, the material has not stayed deformed. Now, if there's a large enough deforming force on the material, the bonds between the atoms start to fracture. So whilst the bonds are still present, the molecules have lost their original shape and pattern, because the deforming force has caused this bonding to fracture. So the material has become inelastic. It will stay deformed. Now eventually, after a large enough deforming force is placed on the object, the bonds will actually break. And we observe this in the real world as the material snapping, breaking, or tearing in half. So, fundamentally, what happens is the molecules can no longer contain the shape that they're in, and the shape loses its rigidity, it snaps. So, what happened is that about 400 years ago, a scientist called Robert Hooke was examining materials and placing deforming forces on them. So he wanted to understand what was going on. So Robert Hooke basically found the following three things. Conclusion number one, and this is for an elastic material. When there's the more the deforming force placed on a material, the more the elastic material extended. Now, when some materials extended, they extended in direct proportionality to the deforming force placed upon them, and then with a large enough deforming force, the material snaps. So, just to clarify what we mean by extension. Extension is the difference in length between the length with the deforming force and the length without the deforming force. So the extension is the change in length of material, or delta L, triangle L. So it's the length with the deforming force minus the length with no deforming force placed upon it. So what Hooke found out was that the greater the deforming force, the greater the extension of the object, and it's also the same for compression as well. Now, in fact, he found that they were in direct proportion. So when the deforming force doubles, the extension doubles. When the deforming force quadruples, the extension quadruples. When the deforming force halves, the extension halves. And this is called Hooke's law. Okay, and as you know, from plotting values on graphs, you can observe direct proportion if the line of best fit of your graph is a straight line through the origin. So when we plot deforming force on the y-axis and extension on the x-axis, it's a straight line through the origin because deforming force and extension are directly proportional. However, this is only for elastic objects. So we say that a material is in its elastic phase if it's a straight line through the origin. So it obeys Hooke's law. When it's a straight line through the origin, it's an elastic object. Now, in some questions in examinations, the graph is a straight line, but it doesn't go through the origin. So what's the common mistake that's been made? Well, the mistake that's been made is that the experimenter measured not the extension, rather the overall length. And that's a big mistake people make when they do Hooke's law experiments. If you measure the length and not the extension, you will still get a straight line graph, but it wouldn't go through the origin. Now, Hooke realised that if there was a large enough deforming force placed on the material, force and extension were no longer directly proportional, so the line would start to curve. And the point at which this occurs on the graph, where you no longer obey Hooke's law, where you are no longer acting elastically, is called the limit of proportionality. So after the limit of proportionality, the material acts as an inelastic. Now, eventually, when there's enough deforming force placed upon it, the object will snap, which is what we call the breaking point. So just to clarify, when you place the force on the y-axis and the extension on the x-axis, you will get a straight line through the origin. That is the elastic phase of the material. At some point, if you keep on increasing the force on the object, the line will start to curve. And when it starts to curve, it's no longer obeying Hooke's law, it's no longer directly proportional, so you've reached your limit of proportionality. Now, after your limit of proportionality, the material has entered its inelastic phase. Now, the gradient of the straight line section, we can actually call the spring constant of the material. So if we place the force on the y-axis and the extension on the x-axis, and as we know, a force should cause an extension, which means that the lines should go through the origin, because if they haven't, it means they've measured length, not extension, right? You should get a straight line through the origin because it's directly proportional, and the gradient of your line is your spring constant. Now, we define the spring constant as the amount of force needed to extend the object by 1 meter. Basically, it's how stiff an object is. The stiffer the object, the larger the spring constant. The stiffer the object, the more difficult it is to extend, so the more force you would need to extend it by 1 meter. Now, the spring constant can only be taken in the straight line section of the graph because, as the name suggests, it's a constant. So you need your gradient to be a constant, so it can't be curving. Now, if you remember, how to work out a gradient is you make your right-angled triangle on the graph with the line of best fit providing your hypotenuse. Now, try to make your gradient triangle as large as possible because that increases the validity of the results as you're considering more values. So what you do is you say gradient is the change in y over the change in x. So it's the change in force over the change in extension. So it's F over E. So the gradient is a spring constant. So spring constant is your deforming force divided by your extension. Now that allows us to work out the units because the unit of the deforming force is newtons and the unit of the extension is meters. So the gradient, this is the spring constant, has units of newtons per meter. And that allows you to work out the units of any gradient of any line of best fit which you draw. So the units of the spring constant are newtons per meter. So the spring constant is the proportionality constant between the deforming force and the extension it causes. So this means that for a material obeying Hooke's law, the deforming force in newtons is equal to spring constant in newtons per meter times by the extension in meter, which we can symbolize in the following form. F equals K times by E. Now, this equation needs to be memorized for your examination. It is not given to you on your equation sheet, but it's only true for elastic objects. It's only true for objects that obey Hooke's law. Now, when this happens, this deforming force causes work to be done. So this allows energy to be stored in the object as elastic potential energy. So a force that stretches or compresses a spring will do work, and it turns the object into an elastic potential energy store. Now, provided the spring is not deforming inelastically, the work done on the spring and the elastic potential energy stored in the spring are equal to each other. So you can work out the energy stored in an elastic object from the elastic potential energy equation, which you covered in the energy module of paper 1, which is elastic potential energy is a half times by spring constant times by extension squared. Now again, this, as we said before, this equation, not the previous one, needs to be memorized for your examination. So let's have a look at an example question. So a spring has a spring constant of 25 newtons per meter. How much force is needed to make the spring extend by 0.10 meters? So you do force equals spring constant times by extension, 25 times by 0.10, 2.5 newtons. Now just to clarify, make sure you check that your units that given in the question are without prefixes, and they aren't. Make sure you give a unit in your answer if we have newtons, and make sure we give it to the correct number of significant figures. Now in the question, 25 and 0.10 are 2 sig figs, so your answer should be given to 2 sig figs. So let's just recap what we've learned so far. Hooke's law states that the extension of a spring is directly proportional to the force applied provided its limit of proportionality is not exceeded, and the deformant force in newtons equals spring constant in newtons per meter times by extension in meter. And we say the spring constant, which is the gradient of a force extension graph, is the force needed to extend the spring by 1 meter, assuming this limit of proportionality has not been reached. So, just to clarify one last time, for an object that obeys Hooke's law, the line of the force extension graph is a straight line and it will go through the origin, okay, unless length has been measured, not extension. Now, just to clarify, it will obey Hooke's law. It will be elastic when you get a straight line through the origin because it's directly proportional. But if it starts to curve, it doesn't obey Hooke's law. It is not directly proportional. It acts inelastically. Now we can only calculate the spring constant from the straight line section of the graph. So when the object obeys Hooke's law, it's an elastic potential energy store. It's elastic, but it is not the case when it's curving when it doesn't obey Hooke's law because it's inelastic. Now, like we said before, if it's a straight line through the origin, the deformant force and the extension it causes must be directly proportional to each other. So when it starts to curve, when it's no longer a straight line, it's reached its limit of proportionality because it's no longer directly proportional. So you've got your elastic region before your limit of proportionality, your inelastic region after your limit of proportionality, and if you keep on adding the deformant force, it reaches breaking point. So once the material passes that limit of proportionality, it will be acting inelastically. So in this lesson, hopefully you can describe what Hooke's law is, understand what elastic and inelastic objects are, and describe how the spring constant and the elastic potential energy store can be calculated for an elastic object. I hope you've enjoyed today's lesson looking at Hooke's law and elasticity. Have a lovely day and take care.